Okay, here we go. Do you have any questions? No. Okay. Would you like to go over problems from the back of the book? Now, there's a quick way to respond. If you go to your screen there, do you see where it says participants? If you click on that, you'll open up a window, and at the bottom of the window, there's a bunch of choices. And you basically want to use the yes and the no. So, would you like to go over problems from the back of the book? Or back of the chapter, I should say. Still chatting, huh? Okay. Then that's what we're going to do. We're going to go over problems from the back of the book. So I'm going to change my share screen. So you should see my tabletop. And here are some of the problems. Let's see if I can rearrange these. Here we go. So let's go ahead and get started. So this is chapter 2, page 106, number 2. And it asks us to define mass number. What is the difference between mass number and atomic mass? So I'm going to teach you a little bit about atomic mass and mass number and atomic weight and atomic number. So I'm going to add a little bit more to this than what we already have. So there's mass number, there's atomic number, there's atomic mass, which is also called atomic weight. And we want to know what each of these means. So mass number, this is the number of nucleons. Number of nucleons in an atom. So now we have to define nucleon. This is a particle in the nucleus. And when you draw a cartoon of an atom, that would be the nucleus. And the region around it, which is a sphere, is where you find the electrons. So both of these are spheres. So this is the electron region. And here's the nucleus. Okay? All right. So mass number, which is a little confusing because it says mass number and mass is a weight according to us, right? It's really the number of nucleons in the atom. So you count these guys. The particles you can find in the nucleus are protons and neutrons. Okay. So this is not part of the question, but I added it. Atomic number. Atomic number is the number of protons in the nucleus. So if you count just the protons in here, that's the atomic number. When you look at an element like carbon, this number at top is the atomic number. This is usually considered to be the atomic weight or atomic mass. And this is the mass of your average carbon atom. And we say average carbon atom because it turns out that there's more than one carbon atom. Okay, so atomic mass weight is the mass in AMU of a substance. AMU stands for atomic mass unit. There is another abbreviation for AMU, and it is U. I like to use U because it's simpler to write. Okay, so mass number is the number of nucleons, which means the number of protons and neutrons. Atomic mass is how much one of these things weighs. Now, a very interesting thing is that when we look at the relative mass of protons and the relative mass of neutrons, they weigh 1.00 each if we just kind of round it off to 3 sig figs. And so if you have 20 protons and 20 neutrons, this has a mass of 20 AMU. And that's why we call this mass number. All right, any questions? Any questions about that? That's right. 20 protons and 20 neutrons would equal 40 AMU, each having a weight of 1.00, and it would weigh 40.0. Okay? We don't really want to round off just to the ones. That's not really quite what we want to do. The 20 protons and 20 neutrons, those are exact, but the weight of each is not exact. Okay? All right. So that's number 2. Number 4. This is kind of a kickback to the previous chapter. A gold atom has a radius of 145 picometers. If you could string gold atoms like beads on a thread, how many atoms would you need to have a necklace 36 centimeters long? So here's your necklace, and that's 36 centimeters. And here's one of your gold atoms and another gold atom and so forth and so on. And when we look at these gold atoms, from end to end here is not the radius, it's actually the diameter. So we need to know that the diameter is 2 times the radius. So in this case, it's 2 times 145 picometers, and that's 290 picometers. So why did I put the decimal at the end of 290? And the answer is because 2 is defined, so it has an infinite number of significant figures. 145 is measured, so that has 3 significant figures. So when you have infinite significant figures times 3 significant figures, you should get 3 significant figures. If I put that decimal there, then that 0 counts. Trailing zeros with a decimal count. So this has 3 significant figures for the diameter. Now, how do we figure this out? Well, we know that the number of atoms times the diameter should equal the total length. That makes sense, right? The number of atoms times the diameter is the total length. So that means that the number of atoms should be the total length divided by the diameter. And so here, the total length is 36 centimeters. And the diameter is 290 picometers. And we could convert this using conversion factors, but the simpler way to do this is to simply write down 36 times 10 to the minus 2 meters. This is a better description of the distance or length than this. C is a substitution for a number, and it's better to put the number there. But we use the substitution because here we write one character, a C, versus here a 1, a 0, and a -2, 4 characters. So that's why we have these prefixes. It's so that we can write less. Now, pico is 10 to the minus 12. And so here you can see that the meters will cancel. 10 to the minus 12 when you take it into the numerator, it becomes 10 to the positive 12 times 10 to the minus 2 becomes 10 to the 10, and 36 divided by 290. If this were 360, this would be 1/10. So this is a little more than 1/10. So we'll call it 1.5 times 10 to the 10 is our answer. Excuse me, 0.15 times 10 to the 10 is going to be our answer, or 1.5 times 10 to the 9. Now, let's plug this into our calculator and see what we get. I need some light here. Okay, so 36 second EE -2 divided by 290 second EE -12. Now, rather than just tell you the answer I get, I'm going to ask you to do this on your calculator and give me a little signal when you're done. And then I'll write my answer and you can compare yours to mine and see if you like yours. Would you like to see how I put these numbers into my calculator? Okay, so I have a TI 30X2S. I like it because it's inexpensive and it's easy for me to use. So I'm going to show you how to put these numbers in. I'm going to scoot this over a little bit. I'm going to zoom in. I don't want to zoom in too much because I want you to see the keys that I'm pressing. So let me show you how to put 36 times 10 to the minus 2 into my calculator. So I'm going to hit 36, and you might be able to see that up here, 36. And then I'm going to put second EE. And when I put second EE, I get just one E there, not two EEs, or not an EE, I just get one EE. That E means 36 times 10 to the power that follows. So to do a -2, I hit the negative here and the 2 here. Now, what's really neat about using that EE button is that your calculator is putting parentheses around the whole thing. And that's what you want. So that's really parentheses 36 times 10 to the minus 2 end parentheses. Now I'm going to divide by 290 second EE -12. And again, there's parentheses around that. So when I put enter, hopefully I get like 1.5 times 10 to the 9, and I get 1.2 times 10 to the 9. And really I get 1.24, but I'm rounding to two significant figures because of this 36. You can't have a necklace that's exactly 36 centimeters long, but it can be 36 plus or minus 1 centimeter very easily. So that's how you want to use your calculator. It's a lot easier. If you wanted to, you could put parentheses around everything. You could do parentheses 36 times 10 caret-2 end parentheses divided by 290, oop, my bad, parentheses, 290 times 10 caret negative 12 end parentheses, and this should work out and give us 1.2 times 10 to the 9. Let's see if it does. And it gives us the same answer. But we had to do a lot more work to do it this way than to use the EE button. So on this calculator, the EE button is right here above the X to the negative 1. And to get to it, I hit second and then that, and that gives me the EE button. Okay, any questions about that? You found the thumb. Do you see the known? Oh, what does that say? Pone sec. I'm not sure what you mean by that. Oh, 1 sec. Are you trying to find that EE button on your calculator? Okay. Some of the mistakes people first make when they use that EE button is they want to put E10 caret and then the power. The EE literally means, so if I write 36 E negative 2, this means 36 times 10 to the minus 2. And it's really convenient to do this. And this actually means this. And that's super convenient because then you don't have to worry about using parentheses. It treats it as one unit. Okay. I'm going to put that off to the side. So if you look at our answer, 1.2 times 10 to the 9, that's 1.2 billion atoms in a 36 centimeter necklace. And a 36 centimeter necklace is about 9 inches. 9 inches. Okay. Give the complete symbol, including atomic number and mass number of the following. So I'm going to show you a little bit of stuff you need to know about these symbols. So let me scoot this down a little bit so you can read everything. So this is on page 106. So there are things called isotopes. So isotopes are different atoms of the same element. So it could be like twins or triplets or quadruplets, different atoms of the same element. And isotopes of an element have the same atomic number. And that's the number of protons in the nucleus. So if we take a look at an element like hydrogen, that's the atomic number. So any atom that has 1 proton in the nucleus, it's a hydrogen atom. So isotopes have the same number, same atomic number, which is the same number of protons in the nucleus. Okay, but isotopes also have a different number of nucleons. So we know that nucleons are things that are in the nucleus. So if we look at an atom, here's the nucleus. And here, this is the electron region. This E with a negative stands for electron. The nucleus is where you find nucleons. Now, this is a cartoon of an atom. This nucleus is a sphere. So if I put this little window in here reflecting light, you can see that it's spherical. and this is also a sphere. So that's the cartoon version to show a sphere, is you put a little reflective window in it that's curved. Okay, so the nucleus is a little sphere surrounded by the electron region. Now this cartoon is a little bit ridiculous. Let me show you a more accurate picture of where you find the electrons compared to the nucleus. So let's call this the electron region. So how big is the nucleus? It's that little dot right there. That's how big the nucleus is. That dot actually may be a little too big. To give you another idea of how big the electron region is compared to where you find the nucleus, if you imagine the electron region, where you can find the electrons the size of a professional football stadium or baseball stadium or something like that, hockey rink, the nucleus is the size of a pea. So there's a 10,000 times difference in the diameter of the nucleus versus the region where you find the electrons. Okay, so isotopes have the same atomic number, different number of nucleons, and they're of the same element. Okay, so the symbol you write for isotopes is as follows. Now, A is the mass number. That's the number of nucleons. Z is the atomic number. That's the number of protons. It seems quite backwards that Z is the atomic number and it doesn't have the symbol A, right? But that's something we just have to live with. And X is the symbol of the element. There's another way to write this, and I want you to learn that also. This is the standard way, standard symbol. And then there's the shorthand symbol, which looks like this. You put the symbol of the element and its mass number. Now, the reason you only put the symbol of the element and its mass number is if you want to know how many protons an element has, you just look at a periodic table and you can find out. Okay, so now that we know all of this, let's get to A here. A nickel atom with 31 neutrons. So if I look on the periodic table, I see that nickel has this, the number 28 at the top, and the number 58.69 at the bottom. Now they tell us that it also has 31 neutrons. So if we figure out the mass number, that's going to be equal to the number of protons plus the number of neutrons, because they're both in the nucleus. So in this case, the number of protons is 28. The number of neutrons is 31. So the mass number is 59. The atomic number we can find at the top of the symbol on the periodic table, so it's 28. So if we want to write this particular symbol using the standard form, there's the symbol for nickel. That's the mass number, and this is the atomic number. What's nice about this is that you put the bigger number at top and the smaller one at the bottom, because you can actually do something like this. Do a little subtraction, and you get the number of neutrons. The other way to write this symbol is as follows: nickel 58. And we don't write the 28 because you can look it up on the periodic table. So that is your answer to A for a nickel atom with 31 neutrons. How about B and C? What are those answers going to look like? Give me a little thumbs up when you have it. Plutonium is down here. Let me zoom in on this so you can see it a little better. So there's plutonium towards the bottom. And tungsten is this symbol W. Okay, so for plutonium, we know that it's 94. So this is going to be 244 and 94 down here, or plutonium 244. And you can't see that because I'm still zoomed in. So there's the answer to B. And the answer to C is going to look like W, 74 at the bottom, 184 at the top, or W, 184. Are we good to go on? Okay. Number 8 says, please refer to the book. So I'm going to take out my book, page 107. We'll take a look at that. I'm going to zoom in on this a little bit. Let's see if I can find my remote. Here it is. So there's number 8. The synthetic radioactive element technetium is used in many medical studies. Give the number of electrons, protons, and neutrons in an atom of technetium. And then also for radioactive americium 241, give the number of electrons, protons, and neutrons in an atom of americium. So let me show you how to do that. So I'm going to give you a little background to number 8. And the background is subatomic particles. I'm going to have to change my zoom here, find my remote. Okay, so a little bit of background for number 8. Subatomic particles. There are 3 that we're interested in chemistry. There are more than that if you're taking physics, but we're only interested in 3. We're interested in the proton, the neutron, and the electron. The symbol for a proton, there's 2 of them, a P with a positive. The neutron is a N with a 0, and the electron's an E with a negative. For a proton, we also have 1, 1. A neutron, we have 1, 0. And an electron, we have 0, negative 1. Now, when we write elemental symbols like this, the top number is the mass number, which is the number of protons and neutrons. And the bottom number was the number of protons. So you can see that that actually works for a proton. You've got one proton and one proton. That's fine. It actually works for neutrons. How many protons and neutrons? One. How many protons? Zero. It doesn't work for this electron. The zero works because how many protons and neutrons do you have? None. But you can't have a -1 proton. So usually when we look at this bottom number, it refers to the charge on the particle. Protons are +1, neutrons are 0, electrons are -1. So the charge on each of these is +1, 0, and -1. And while we're talking about charge, there are some charge properties that you want to know. First thing about charge properties you need to know is that there's two types: positive and negative. For positive, we use a plus sign. For negative, we use a negative sign. Opposites attract. So a positive is attracted to a negative, and like charges repel. So a negative is repelled by negative, a positive is repelled by positive, and charges are additive. And that's going to be important for us to answer this number 8, which was about americium 241 and technetium 99, I think, or 91. I can't remember which. I want to say 99. Okay, so the other things we want to know are the mass of each of these in atomic mass units. And a proton is really close to 1.00 atomic mass units. It's probably 1.01, but 1.00 is close enough. Neutrons, 1.00. They have the same relative mass. Electrons are about 0.00 on this scale. So electrons are, for all practical purposes, nothing compared to these guys. In fact, though, an electron weighs about, well, you need about 2,000 electrons to make one neutron by mass. So that's a lot. Oh, I see something about back out on Zoom. I think I've done that. Is that right? Okay. Now the mass in grams, and these are not numbers that you want to memorize. They don't memorize these. I think it's 9.01, maybe a little different. And here you can see that we've got -24, and this one's -28. So this is quite a bit less massive than these guys. And their location is the nucleus, and surrounding the nucleus. Okay. So now we're ready to answer number 8, where we're supposed to take a look at technetium 99 and americium 241 and say how many protons, neutrons, and electrons. So we're going to look first at technetium 99, and we're going to do protons, neutrons, and electrons. So technetium 99 is TC 99 at the top. And when we look at our periodic table, we can see technetium right here, which is number 43. Now, when they ask us about this technetium atom, they're talking about a neutral atom of technetium. That is to say, no charge. Okay, so this guy has 43 protons. That's the atomic number. How many neutrons? Well, I can do a little subtraction here to figure out how many neutrons. 9 minus 3 is 6. 9 minus 4 is 5. So there's 56 neutrons. Now, if this guy is going to be neutral because we're talking about a neutral atom, how many electrons does it have to have? Well, if it has 0 with 43 protons, each with a +1 charge, the total charge on this guy would be positive 43. So to make it neutral, we're going to have 43 electrons. So there's your answer. Now, what is the mass of this particular atom in AMUs? And if you recall, a neutron is 1.00. A neutron is 1.00. A proton is 1.00. And since we have 99 of these, this is 99.0 AMU or 99.0 U. Any questions about how I got the mass, the number of electrons, neutrons, or protons? Okay, good. So I want you to do the same thing for americium-241. I want you to write it in the standard way. I want you to tell me how many protons, neutrons, and electrons, and the mass. When you're done, just give me a thumbs up. Oh, and let me help you out with americium. It's down here on the periodic table towards the bottom. $95. Okay, so the number of protons is 95. And if we write americium-241 95, we can figure out how many neutrons by subtracting the two. So 11 minus 5 is 6, 13 minus 9 is 4, and then 146. And of course, these two numbers added together should be 241. The number of electrons is the same as the number of protons. And this guy has a mass of 241 AMU. And that's all there is to it. We good to go? Okay. Let's take a look at number 10 in the book. Number 10, I certainly don't want to draw this out, but I want to talk about this a little bit. So this is a cathode ray tube, and this is one of the devices that they use to learn about electrons. And this here is an anode. It's called an anode because it attracts negatively charged particles. And so here the anode is positively charged because opposites attract. This is the cathode, and cathodes are called cathodes because they attract positively charged particles. And to do so, they have to be negatively charged because opposites attract. Now, with the cathode ray tube, what happens is that the cathode generates electrons that go to the anode. So this is really an electron gun that's shooting electrons. In this cathode ray tube, you see this thing that says gas molecules. So it could be a gas molecule, it could be a gas atom. And we know that atoms are made out of neutrons, protons, and electrons. And molecules, therefore, are also made out of neutrons, protons, and electrons. And we know that electrons are really tiny compared to protons and neutrons. So what can an electron do that's going from the cathode to the anode? What can it do when it strikes a gas molecule? Well, it can't really do much to the nucleus because it's too big. It'd be like throwing a ping pong ball at an elephant. On the other hand, what could an electron do to an electron on an atom that they're both the same size? And the answer is one of those electrons could knock another electron off of the atom. So imagine if you have a technetium atom with 43 protons and 43 electrons, and you knock one off, and now you have 43 protons and 42 electrons. One more proton than electrons. What's the charge on that technetium atom going to be? +1, and that's how you create a positive ion. So that's how you create also something called a cation. Cations are positive ions. So this is the process by which you can make cations in a cathode ray tube. Is an electron knocks an electron off of an atom. Any questions there? Okay, we're good to go. Let's take a look at number 12. In the early 1900s, John Dalton proposed that an atom was a solid, massy, hard, impenetrable, movable particle. So when I think solid, and I need to zoom out. So this is on page 107. John Dalton proposed that an atom was a solid, massy, hard, impenetrable, movable particle, which sounds to me like a rock. So there's your atom, a rock. Critique this description. Before we critique this description, I also want to give you J.J. Thomson's idea of an atom. J.J. Thomson thought that an atom was a mushy material like plum pudding that had electrons in it. And surrounding the electrons was this pudding of positive charge. So at this time, they didn't really know about protons. They knew about electrons. So here, the reason they call this the plum pudding model is because the electrons were like raisins in plum pudding or plums in the plum pudding. Which I'm going to be honest, sounds pretty disgusting to me, but I guess they didn't have chocolate pudding back then, which means life was horrible back then. You know, this is like the 1870s and stuff like that, really long time ago. Okay, so this is the plum pudding model. And these are two ideas of the atom. So a guy named Rutherford came along, and he decided he was going to test these models of the atom. So he had these things called alpha particles, which had a +2 charge. And he shot these at the atom. So I'm going to move this up. Here's the plum pudding model. So if you have this type of atom, and this guy is not as massive as an atom, it's far less massive. This is hard like a rock. What's going to happen to this particle when it hits the rock? And the answer is it's going to bounce right back. If you have the plum pudding model and you know that these electrons are really, really tiny compared to this guy, they don't really know what this guy is. It's just this thing with a +2 charge. You shoot it at here, and the expectation is going to go straight through like a bullet through a piece of paper. So these are the hypotheses for what you would expect for each situation based on the Dalton theory and the Thomson theory. So here's what happened. When he first did this experiment, so here is the material that he shot the alpha particles through. He used gold foil. And the reason you use gold foil is because you can make it very, very thin, 1 atom thin. It's unreactive, so you don't expect any sort of chemical reaction. And you can see what happens here. So it's either going to go straight through or bounce back. And this is what he found. 99.9% of them, bigger than that actually, went straight through. So that sounds like the plum pudding model. However, he found that, and this is your detector here, he found that some of them hit over here, some of them hit over here, some of them hit over here, not very many, some of them hit over here. And when you get so many, whoops, I should do that. When you get so many that are hitting off center, the natural question is, how far are you going to see them? So they extended the detector so that it went behind the source, and they noticed that some of them hit back here. So it seems like a combination of something that's hard and something that's soft. Now, what's the best explanation for something like this where most of them go straight through and very few of them get bounced around? And the most reasonable thing to say is, well, you know what? If most of them go straight through, it's because an atom is mostly nothing. So the alpha particle goes right through. It's mostly space. So space means nothing. Now for the nucleus, some of them hit the nucleus and bounce right back. And that's probably because the nucleus is very dense like this rock. Now, if this alpha particle has a +2 charge and the nucleus has a positive charge, since like charges repel, that would explain why some of them get close to the nucleus and come off at an angle. So this is Rutherford's idea. So this is Rutherford. Based on his experiment, it kind of proves these two hypotheses wrong. And you come up with a new hypothesis where you use the simplest explanation for what you observe. The reason the particles don't deflect is because atoms are mostly just space. The reason some of them come right back is because they hit something really dense. And we call that the nucleus. And the reason some of them deflect a little bit is because of charge repulsion. All right. Any questions about these ideas of the atom? So this is the one we accept now, where basically you've got a nucleus in the center and an electron cloud around the outside. Okay. So we're going to move on. So next we have, what is the mass of one O atom in grams? And we have the mass of an O atom is 15.999 U. So one O atom is equal to 15.995 U. What is the mass of one atom in grams? So here, I'm going to put a little 16 at the top there. We have to know that one atomic mass unit is 1.66054 times 10 to the minus 24 grams. I think that's the value. Let me double check. This is towards the beginning part of the chapter. .66054. So that's one atomic mass unit. So the interesting thing about this is this applies to anything. It's kind of like this, where we say 16 ounces is equal to 1 pound. So what does the ounce and the pound apply to? Anything. 16 ounces of steak equals 1 pound of steak. 16 ounces of water equals 1 pound of water. 16 ounces of dirt equals 1 pound of dirt. So what does this apply to? The same thing. One atomic mass unit of dirt equals 1.66 times 10 to, or 66054 times 10 to the minus 24 grams of dirt. Now, naturally, when we're using numbers like this, what are we referring to? We're referring to atoms and molecules. So one atomic mass unit of a molecule is 1.66054 times 10 to the minus 24 grams of that molecule. So this is a conversion factor. So we know that 1O atom, and that's the 16 isotope, is equal to 15.995 atomic mass units. So we're going to multiply by this so that we can get grams. And naturally, we're going to put one U on the bottom so that the U's cancel. And we're going to put 1.66054 times 10 to the minus 24 grams on top. Here we have 5 significant figures. Here we have 6. So we're going to be allowed 5 significant figures. The way I'm going to put this into my calculator is I'm going to put 15.9995. Well, I got to clear 15.9995. Well, too many nines. 995, not 9995, times 1.66054 second EE negative 24. And here we kind of want to estimate the answer. 1.66 is like 1 2/3. So if this is 16, 1 times 16 is 16. 2/3 of 16 is about 10 or 11. So 11 plus 16 is 27. So I should get 27 times 10 to the minus 24, or 2.7 times 10 to the minus 23. That's my estimate. So I put this into my calculator, and sure enough, I get 2.6560 times 10 to the minus 23 grams. Any questions here on the gram mass of one O16 atom? Or are we good to go? Good to go? Okay. So, naturally occurring silver exists as 2 isotopes having mass numbers of 107 and 109. How many protons, neutrons, and electrons are there in each of these isotopes? And what is their mass? So I want you to write the symbol of each of these, the standard symbol. I want protons, neutrons, and electrons, and I want the mass of each isotope. So let me know when you're done. Silver has this symbol, Ag. Okay, great. So we're going to have silver 107, and the atomic number of silver is the number at the top in the square, and it's 47. So for protons, this guy has 47. For electrons, it has 47. For neutrons, we're going to subtract 47 from 107, which is 60. How many significant figures in each of these numbers? And the answer is they're infinite because they're counted. The mass of this guy is 107 AMU. How many significant figures here? And the answer is 3 because the mass is not counted, it's weighed or calculated. The other silver is going to be 109, 47. And for protons, we're going to have 47. For electrons, we're going to have 47. And for neutrons, we're going to have 62. 2 more neutrons than over here because the mass number is 2 more. And the mass here is going to be 109 AMU. Now, if we look at the silver element here on the periodic table, on the bottom here it says 107.9. Okay, so this is an interesting number, 107.9. What is the average of 107 and 109? And the average is 108. So if for every one silver 107 isotope, you had one silver 109 isotope, 1 for 1, the average mass should be close to 108. And that's really close to 108, but it's not 108. So what does this number mean? Because it's lower than 108. And the answer is, well, there's more silver 107s. Let's go to an extreme. Let's say you have 2 isotopes and one weighs as much as an elephant and one weighs as much as a mouse. And you average the 2 together. If there's 1 and 1, what are you going to get for the average mass? Well, maybe a rhinoceros. That seems to be about halfway between an elephant and a mouse, okay? But what if there's 10 elephants for every 1 mouse? What will the average weight be? And the answer is it's going to be closer to the elephant. And what if there's 10 mice and only 1 elephant? The average is going to be closer to that of a mouse. So here, the fact that this number here, which is the average mass of a silver atom, the fact that it's closer to 107 than it is to 109 means that there's going to be more 107s than there are 109s. That amount that we have of each of these is called the percent abundance. Okay, we ready to move on? Good to go? Okay. So this is a very easy one. Which of the following isotopes are of element X, the atomic number for which is 9? So if they say the atomic number is 9, they're talking about this number at the bottom. So which of these are part of this particular element? And the answer is this one here, this one here, and this one here. This is impossible. Why is this impossible? The number at top is the number of nucleons. Number at the bottom is how many of those nucleons are protons. The number at the bottom can never be larger than the number at the top. At best, they can be equal, but they can't, the number at the bottom cannot be larger. So here's your answer for 18. That's a pretty easy one. Strontium has 4 stable isotopes, 84, 86, 87, and 88. So if we look at those, Here's strontium 84. Here's strontium 86. There's 85. Here's strontium 87. And here's strontium 88. And this guy weighs 84 AMUs, 84.0. This is 86.0 AMUs. This is 87.0 AMUs. And this is 88.0 AMUs. And they say that the average mass is 87.62 AMUs, which is the most abundant. And remember the elephant and the mouse story? The average is going to be closer to the one that's most abundant in many cases. So the only way for the average to be so high is that there has to be a whole lot of 88s. So strontium 88 is the most abundant because its mass is closest to the atomic weight. And a lot of people say atomic mass. Any questions about that? We good to go? Okay, this next one, we're going to try and get 2 more done. This next one says, verify that the atomic weight of magnesium is 24.31, given the following information. So I'm not going to look at this information right now. I'm going to show you how to calculate atomic weight. So AW, atomic weight, is equal to the sum of the mass of the isotope times the percent abundance of the isotope divided by 100. So if this question were asked on the exam, I would definitely expect to see this as part of your answer. The next part I would not expect to see as part of your answer, but I'm going to write it out. In this case, we have 3 isotopes, magnesium 24. So I'm going to put the mass of magnesium 24. The percent abundance is 98, and then I'm going to put percent abundance. I'm going to put A instead of abundance. Percent abundance of magnesium 24 over 100 plus the mass of magnesium 25 times the percent abundance of magnesium 25 over 100 times the mass of magnesium 26 over, or times the percent abundance of 26 over 100. Now, the next thing I'd expect to see in your solution would be this. 23.985042U. So I've got the mass and I've got the unit. 78.99 over 100. Now, I know in math classes, they generally teach you that if you have a percentage, move the decimal over 2 places. We don't do that in chemistry, not in my class, because I see too many people moving the decimal the wrong way. Like if you have a 0.0052% and you move the decimal over, half the people in class will say that that's equal to 0.52, and it's wrong. Because they can't fathom moving the decimal over and putting more zeros in there. They just go, no, that can't be the case. So we don't bother with moving the decimal over. We divide by 100 because the definition of percentage is not move the decimal over 2 places. The definition of percentage is divide by 100. And when you divide by 100, you can see clearly that I'm going to take this number and make it smaller. So I'm going to move the decimal to the left. But we don't need to worry about that because we're just writing over 100. I've got the unit. Now you might be wondering, what are the units for percentage? And the answer is, for percentage, the unit on top is the same as the unit on the bottom, so they cancel. So that's the nice thing about percentages. We don't have to put units in there. Okay, I would expect to see this as part of your answer. Now let's do the work here. 23.985042 times 78.99 and divided by 100. So here I get 18.94578. And here, since I have what, 1, 2, 3, 4, 5, 6, 7, 8 significant figures, 4 here, and since percentage is defined as over 100 exactly, that's infinite. This is good to that 4 right there. And I'm going to put U. This one, I don't even need a calculator because I'm going to take 1/10 of that, which is 2.498587 U. And this is going to be close to 2.59 because that's close to 10, but it won't be quite 2.59. Let's see what we get. 2.5982.82593 times 11.01 and divided by 100. I did something wrong because I got 0.286. So clearly I did something wrong. 25.982593 times 11.01 and divided by 100. That's better. 2.86068 AMU. And this also is going to have 4 significant figures, so that's good to there. This is going to have 4 significant figures, so that's good to there. So when I add these numbers together, you can see that this is precise to 2 numbers over from the decimal. This is precise to 3 numbers over. This is precise to 3 numbers over. I'm going to round to whichever is least precise, which is 2 numbers over from the decimal. So I'm going to round to right there. And I believe I get 24 point, let's see, plus 2.4985837. And then plus 18.94578. And I get 24.305, which rounds to 24.3. And here, that's U. So everything you see blocked off is something I would expect to see as part of your answer on an exam. Any questions about that? Or are we good to go? Okay, this is going to be the last one that we look at. Number 24 says europium has 2 stable isotopes with masses of 150.91 and 152.92 respectively. Calculate the percent abundances of these isotopes. So they want us to calculate the percent abundance instead of the other way around, and that is calculating the atomic weight. So we're going to use the same formula. Atomic weight is the sum of the isotope mass times the percent abundance of the isotope over 100. Okay, so here's the way I'm going to solve it. I'm going to say the atomic weight is equal to the mass of europium 151 times X, where X is equal to the percent abundance of the isotope over 100. And times the mass of europium 153 times Y, where Y is the percent abundance of this isotope divided by 100. So X is equal to the percent abundance of europium 151 over 100. And Y is equal to the percent abundance of 153 europium over 100. Now we have a name for this where you take this divided by that, and it's called the fractional abundance. So I'm going to call that FA, the fractional abundance. Okay, so X is the fractional abundance of europium 151. Y is the fractional abundance of europium 153. Now this equation is impossible to solve when you have two variables in one equation. So we solve this with a system of equations. We need another equation that relate X and Y. Well, if you have percent abundances for each of these and you add them together, you get 100%. What happens when you add the fractional abundances together? You get 1. So X plus Y is equal to 1, which means Y is equal to 1 minus X. So now we have the atomic weight is equal to the mass of 151 europium times X plus the mass of 153 europium times 1 minus X. And then what I would do is this: atomic weight is the mass of 151 europium times X plus the mass of 153 europium times 1 minus the mass of 153 europium times X. So here you can see that I probably want to take this and put it on this side, minus mass of 153 europium. And on this side, I'm going to divide X out and get mass of 151 europium minus the mass of 153 europium. Okay? And then we can solve for X because, and I'm going to move this up here like this, X is going to be the atomic weight minus the mass of europium 153 over the mass of europium 151 minus the mass of europium 153. Now, you might be thinking to yourself, this mass is going to be smaller than that one, so the bottom's going to be negative. Oh no. And you're right. This mass should be smaller than that one. We can see that it is based on the data. But what is the atomic weight going to be compared to the mass of europium 153? This will also be smaller, so the top will be negative. So you'll have a negative divided by negative, and that'll give you the fractional abundance of europium. And so here, if X is equal to 47 or 0.47, that means that the percent abundance, using the formula up here, X is the fractional abundance. So we have fractional abundance is percent abundance divided by 100, which means that the percent abundance is the fractional abundance times 100. So if we got this, we would get 0.47 times 100, which would be 47%. Okay, so this is a some algebra 2 stuff you've done before where you have two separate equations and you combine them together. And I would expect to see this. I'd expect to see that and that. And then I'd expect to see your answers, because I don't want to see all this stuff. I don't want to see how you manipulate the equations. That's just algebra. And my assumption is that you have mastered algebra. Fair enough? Capiche? Okay, or in Japanese, that would be wakarimasu. And you would say, hai, wakarimasu. Oh, I'd say, excuse me, I forgot my Japanese. I'd say, wakarimasu ka? And you would say, wakarimasu, which means I understand. Or I know. All right? It's been a long time since I spoke any Japanese. You want to hear a joke? Is the thumbs up? You want to hear a joke? Okay, so here's the joke. My mom's Japanese. And she used to say something to us kids all the time. And it was urusai. And so naturally, being a child and knowing that my mother loved me, I thought urusai meant I love you. And so my Japanese grandmother came to visit and I wanted to tell her that I loved her. So I said, urusai. And man, she just gave me a look like you'd never believe. So I asked my mom, what does urusai mean? She goes, it means bug off. So apparently my mom was not telling me that she loved me. She was telling me to bug off. Actually, I knew what urusai meant. It means bug off, because her tone definitely gave you the bug off vibe. Okay, now you want to hear the last Japanese joke I have?
Go for it, Tony.
Okay, here's the joke. Do you know what EA means in Japanese?
No.
Good job.
Keep your day job. Hey, thanks, Tony. I'll see you again Wednesday night.
Yeah.
Okay.
Have a good one.
You bet. Thanks, man. Bye-bye.